Good morning, everyone. Welcome to the Physics 131 online version. Today we'll start with our first online lecture series on Chapter 9. And in Chapter 9, we're going to learn about work and energy concept. This first lecture series is designed that you will read along with a textbook, and it's designed that you, as you read along the sections, that I'll provide commentaries and explanations and derivations that might be details might be missing from the textbook. So I strongly encourage you to read along the reading assignments each time. Today in particular, the reading assignment is the first two sections of Chapter 9. As you can see from my OneNote screen here, today the learning objectives are twofold. Number one, what is work and why do we use this concept? And number two, what is kinetic energy and how it relates to work? Okay, so these are the two objectives that we're going to cover today. Let's begin with the concept that we already know as well. So let's begin with Newton's second law. The Newton's second law, as we learned from class, states that the net force is equal to ma. And I want to remind you that the left-hand side here, these are not one force. This is a net force, meaning the summation of all the forces, relevant forces known, that are acting on a single particle on the right-hand side. Here, this is a single particle. The sum of the forces causes this single particle to accelerate with the acceleration a. That's Newton's second law, and we've been using this law on numerous occasions already, right? So we encounter a situation, we draw a free body diagram, and we identify all the relevant forces, and we sum them up and set that equal to ma in various situations. And that's a very powerful tool that, as you have used it also, that the Newton's law, as long as you know the sum of forces, you can numerically, analytically calculate the acceleration of a single body object given its mass. All right, so, but the important prerequisite of using Newton's laws, particularly Newton's second law, as I mentioned, is that we must identify all relevant forces. And this, depending on the situation, may or may not be practical. Most of the examples we dealt with thus far, that the forces were constant, and hence so was the acceleration. And the forces were easily identifiable in most of the times. Force of gravity, the spring force, the friction force, and etc. But what if we enlarge now the context here a little bit? What if we cannot identify or well describe individual forces? What if the forces given are nonlinear or they're changing forces? Well, what do you do in that situation? So we're going to gradually expand our toolbox here, and that's, just keep that in the back of your mind. That's kind of the motivation why we want to develop a new tool called the work and energy. So let's start with an example of an inclined plane. We have solved numerous occasions of how to solve an inclined plane here. So let's assess the situation. Here we have an incline here. Let's call this angle is theta. And this box or crate is sitting on it here. I already drew the three arrows here. First, for forces, I will identify as a force of gravity. And then you have the normal force that's perpendicular to the surface. And then you have the friction force, kinetic friction force, that is causing it to slow down as it slides down the slope, depending on the angle. Now we identify these individual forces. That's what we usually do. Then we write the sum of forces in x and y, because these are two-dimensional problem here. All right, so in x, we have this, remember this tilted axis orientation, this along the slope is going to be the x-axis here. So here you will have the x component of a force of gravity. you guys remember how to write the x component regarding the angle theta. And that is force of gravity, mg, but g relates to the angle of the slope, and the x component in a tilted axis scheme, you have mg sine theta. Actually, let's call that minus. Let me erase that here. Try to write it once again. All right, so let me start writing minus mg sine theta. Then you have, this is a minus direction, then you have a plus force of friction. And this is dynamic case, so we have that is equal to ma. And remember, this mass will be the mass of this object, which is the only object that is considered here. And then you have the acceleration along the x-axis, because we're dealing with the sum of forces in the x-axis. Let's go one step further. The force of friction. Any force of friction could be written as the coefficient of friction times the normal force. So this you can substitute in here, and then it's left for us to find out what the normal force is, and then we can solve this equation, everything within this equation. The y-axis, we have the y component of the force of gravity, and remember, see, we decompose into these two, and this angle and that angle is identical. This is a review, should be a review for you. So the y component in this tilted axis, you have again minus mg cosine theta. That's the y component of force of gravity mg, plus normal force, that is pointing straight up on the opposite direction. And since this box is not supposed to be moving up or down, this is a static case, so this is equal to 0. So again, from the y-axis, we always can infer the normal force, which is mg cosine theta. Knowing that, now we can substitute here and solve everything from the x-axis. So let's continue writing that here. We had minus mg sine theta plus mu k mg cosine theta, and here I substituted the mg cosine theta into the normal force here, and that is equal to ma x. All right, so we have mass involved in all sides, so let's cancel that out by dividing both sides by mass. So we have here minus g sine theta. Let me drop the subscript since that's the only one we're dealing with here. Cosine theta is acceleration. And once we have the acceleration, now take a look at here. We're assuming that the angle theta is constant. So this is a constant, g is a constant, mu is a constant. So everything on the left-hand side is basically numbers, constant. Hence, the acceleration also must be constant. And because they are constant, now we can utilize the wonderful kinematic equations to describe the position or velocity, or even the velocity square, etc. And the important prerequisite of using the kinematic equations was that the acceleration has to be constant, which is in this case, and by using these we can solve all kinds of different physical parameters. Its position, its velocity, and etc., and its displacement, etc. Right? Now this all is hinged on the fact that the acceleration is constant, which, if you think about it, the left-hand side has to be constant in order for the right-hand side to be constant. So all the forces given here need to be constant. In this case, they are. the force of gravity is mg. Mass doesn't change. G is a constant. This is a constant force. Same as normal force, mg cosine theta, as long as theta remains constant. Now, the situation could be that what if theta is changing? What if the forces are no longer constant forces? Then you will have the normal force that is changing, perhaps in time. And hence the normal force is non-constant force. Your sum of forces will also be non-constant force. And in this case, we can no longer use the kinematics equations because this depends on the acceleration being constant. And this becomes a differential equations in time-dependent equations, which is much more difficult to solve if it's not possible to solve analytically. So that's one example where we could quickly, the problem could become more complex from what we are used to solve in class. Another example is like this. So to come back here. Now remember, all of the problem set that we have used, we have situation where the motion, the direction of motion was either horizontal or straight vertical, or like an inclined plane, diagonal, or a uniform circle. These examples basically include all of the direction of motions that we dealt with. And you can see that this calls for a constant forces being uniform in its directionality. Now consider an example here. Let's say you have someone is riding a skateboard and he's going to go down this curved path. In this situation, describe the normal force for me. When the skateboard is here, let me change the color. Click. Oops. The normal force would point this way. When the skateboard arrives at this point, the normal force is pointing straight up, and here it even changes its directionality. So you see, in this case, we have a surface, a path of motion where it forces the normal force to be changing all the time. And again, we cannot simply set up sum of forces and use a kinematics equation to solve it because, first of all, acceleration will not be constant, and so will other forces also will have non-constant components. So dealing with a situation like this, now solving a problem like this is not particularly a rocket science, right? It's not particularly too difficult, but simply just using the Newton's law, we might run into unnecessarily obstacles to solve this. So we're going to develop a new tool dealing with situation where the forces involved may not be constant or not well described, and then we're going to develop a new physical mathematical tool that can handle such situation. And we're going to start developing a concept called work and energy. So let's begin by doing some mathematical derivation. Okay, so I'm going to derive here, starting from Newton's second law. I'm going to derive mathematically the concept of work and kinetic energy. So take a look at here. All right, so let me see if I can do this by typing. We know that the F sum of forces net force is equal to ma. And ma, acceleration, is derivative of velocity in time. So I can write this, right? Mass times derivative of velocity in time. That's the acceleration. Change of velocity in time. That's acceleration. So this is nothing but stating the definition. Okay? Now, let's consider situation here. So take a look at this diagram here. We're going to simplify, okay? We're going to start from a simplified version, and then we're going to go more general later on. So, the first situation is that you have a particle sitting, and the force applied to that particle bears the same directionality as the particle would move. So the particle here has initial velocity traveling this axis. The textbook uses xs, which could be x or y or any combinations of the tilted axis. It's just a generalized form of the axis, but it is moving in one direction, and the force applied to it happened to be exactly parallel to that direction, okay? So as the force is pushing this particle, it will increase its velocity as the particle moves along this axis. So at this point at final, the force applied here is still constant, okay? The force is constant with the simplified version. And then the velocity, starting from initial, traveling this displacement delta s, at this point it will have an augmented velocity due to this constant force applied. Okay, so that's the situation here. Now, of course, this takes place in time, right? So starting from the initial to the final, you can set this instead of initial position in the final position, you can also set it as initial time and final time. However, what we're going to develop is we want to have an expression that is time independent. Time independent. Okay, we want to get rid of the factor of time. Okay, and why it will become a more apparent later on. So just follow with me. So remember, the purpose of this derivation is we want to get rid of time. Okay, we want to describe the expression of the motion that is time independent. Okay, so now let's consider in that situation here. You see that velocity. Let me switch back to blue. All right, so the velocity is described in this case as a function of position. It's a terrible way of writing velocity. All right, velocity is described in terms of position. Because you can see here, depending on the position of the velocity from going from here to here, the velocity will increase, right? So you can describe the velocity as a function of position. But of course, this position will change in time. So the position itself and the velocity is also a function of time. We just want to ignore it. But we want to describe this in terms of position. So what we're going to do, we're going to borrow a mathematical tool from calculus called a chain rule. Chain rule in calculus. And this, if you have not been familiar with this concept, I strongly encourage you to take a look at this concept. You can easily Google up the chain rule in calculus. Also, you can look up multivariable chain rule, and then you will see the expression of the property that we're going to use here. So the chain rule in calculus, and this is already proven by mathematicians in the past, so we don't have to go through all the proofs. We just can trust it because statement of logical fact. So if you take the derivative of time, or it doesn't have to be time, but let's just call it that you have a function that is a function of x, but the inner variable of this function itself is a function of the second variable called t. In this case, let's just assume this is time, okay? So you have a function f that is a function of x, and the x is a function of time. And now if you take the derivative of the original function respect to t, which is the variable of the inner function, then the derivative, the expression looks like this. So you take the first derivative of the original function respect to x, because that's what this function is defined as, right? Defined of. And then you multiply the second derivative of the inner function x respect to t. And that is a chain rule in calculus. So what we're going to apply here is that we're going to take the time derivative of a velocity that is a function of position, but the position is a function of time at the same time. So by using this chain rule, we can write exactly as this dot ds dt. Okay, just simple application of this chain rule in calculus. All right? So we're going to use this property because here, this is now going to be written like this. You have m dv ds divided by dt. Okay, just simply writing down the property that we have derived here into here. Now take a look at here. ds dt. S is any position x's, x, y, z, tilted x's, etc. What is ds dt? That is velocity, right? The time derivative of a position is velocity. So this reverts back to, let me just copy here, times velocity respect to that axis. All right? Okay. So let's see here. Now, let me just write it here one more line. We started with a sum of forces. And in this particular example, we have only one constant force that is equal to Fs. That's my net force. And that was equal to Ma, which in turn equal to this over here. Okay? So now we have this expression as highlighted here. The constant force is equal to m dv ds multiplied by velocity respect to s. Okay? Now we see we have here dB with the velocity and we have forces with ds. So we're going to perform what we did several times in the past. We're going to perform separation of variable technique here. So we're going to separate sum of the force Fs, and we're going to send this ds on this side, and we're going to keep mvs dv on the other side. I have separated the derivative variable dv ds. They're separated on either side of this equation. Okay? And then once you have separated, you take the integral on both sides. Here is s, so you have an initial position, final position, you have here initial velocity and final velocity. Let's work on the right-hand side first. The right-hand side, you see this is mv dv, and you have the integral. So m is a constant, and you're taking a derivative of v dv initial and final. And this becomes m 1/2 v square, and you have here v final minus v initial. So this becomes 1/2 mv final square minus, we're running out of space here a little bit, 1/2 mv initial square. Okay? Now, the concept number one, we will define kinetic energy. Okay, kinetic energy is energy of motion. Any particle with a mass m with a velocity will have energy. Okay, so the kinetic energy is defined as 1/2 mv square. Okay, this is conveniently the expression that we have here. So this simply becomes kinetic energy final minus kinetic energy initial, because that subscript will go for the velocity. And what's the final minus initial? That's change in kinetic energy. So it's delta K. So that's the right-hand side of this integral. The left-hand side of the integral, which is the integral of force dotted with ds. So you're taking a force and taking the integral of the force respect to the position. Okay, you're taking the integral of the force respect to the position. That is, we're going to define. This is work. So the work is what a force causes a change in position of a particle. Now let me give an illustration here. So in our case, we have constant force, right? So it's simply F, and you have 1 times ds, S initial, S final, which is F, S, S final, S initial. And that is F times delta S, because this will be S final minus S initial, which is delta S. So in this simplified format, our work, which is the left-hand side of this integral that we define, is equal to the magnitude of the force multiplied by the displacement of that particle. That's why a work, conceptually, by looking at the left-hand side, is an integral of force respect to position, which is what a force causes a displacement, or change in position of a particle. And we refer work as usually in a passive form, meaning that we say usually work is done by a force on a particle. That's how we usually will say. So in this case, a work is done on this particle with mass m by this force causing this displacement of that particle. We call that a work. And equivalently, the right-hand side we derive as a change in kinetic energy. So this is the important statement here. Work done by a force on a particle is equivalent to the system's change in kinetic energy. Okay, let me write it here again. The work, in this case, cause a displacement of the particle. Okay, a force caused this displacement. So the multiplication of that is equal to work, and that's equivalent to the change in kinetic energy of that particle. So here you have a relationship of work that we just defined to the change in kinetic energy. So how is this going to be useful? It will become more and more apparent as we deal with situations. But we're going to start today by examples that you have seen before, the one that you're able to solve knowing nothing about work and energy. And we're going to solve that using work and energy and just to get ourselves comfortable with it. And later on, we will have a situation where it will be more difficult to solve using just Newton's laws. And you have to resort to using work and energy concept. Okay? Another important concept is we have to determine the sign of work. What does a positive work and what does negative work would mean? Now, for today, if when the force direction, force is a vector. When the force direction is parallel, and not just parallel, but in the same direction as the directionality of the displacement, then the work is positive. So positive work, actually, so let me write down here, let's see. So positive work means that the directionality of the force applied is in the same direction as the displacement. And you can refer the negative work would be that the directionality of the force applied is in the opposite direction as opposite direction of the displacement. Put direction of the displacement. Okay? Positive, negative. So going back to this example here, this force will cause this particle to, let me write that, say that in passive form. The work done by this force on this particle is positive in this case because the directionality is the same as the displacement of the particle and with the directionality of the force. If the force applied is this direction, but this particle actually have displacement going this direction, then we say the work done here is negative. And I'll give you more example later on. Okay, now, what we calculated here is technically a work total. Write that down here. Okay. So sometimes you could have more than one forces being involved in a situation. Here in the previous example, we just have one force, but you could have more than one forces being involved. In that case, each of the force will have individual work done on the system, on the particle. So in that case, you will have work done by the force number 1, work done by force number 2, plus how many forces are being involved. They will each have a possibility of having a work done on the system. Now, the description that we have derived here, when you take this, if you have more than one forces, this becomes summation of forces. So you have individual forces here. So this leads to work total, which equal to work 1 plus work 2 plus 3 and etc. And that all combined is then equal to change in kinetic energy of the system. Okay, this concept I will also elaborate it with other examples. Let's take a look at this example over here. Example 9.1 from your textbook. Example 9.1. So a 5 kilogram cannonball is fired straight up at 35 meters per second. What is its speed after rising 45 meters? Now, this situation here, we can easily solve this by just simply using Newton's laws, because the initial velocity, and once the cannonball leaves the cannon, it's subject to only one constant acceleration, which is gravitational acceleration 9.8, and then you know the displacement, so you can simply use final velocity is equal to initial velocity 2a delta y. So if we square initially 35 square minus 2 9.8 and then the displacement 45, and here you only have one variable, so you can easily solve this problem by using just Newtonian laws. But to illustrate the point from a point of familiarity, let's try to solve this using work and energy. Okay, and in particular, the question will ask you how much work is done by gravity. So in this case, how many forces are being involved after the cannonball leaves the cannon? Okay, after the cannonball leaves the cannonball is subject to free fall. The gravitational acceleration will try to pull it down. So in the free body diagram, you only have one force present here, which is equal to mg. So work, and in this situation, you can easily see that the directionality of the force and the displacement is not in the same direction, but it's in the same axis, right? The same axis. So we can simply use the result that we derived above there. The work will be the force, the magnitude of the force times the displacement. So in this case, the force is minus mg. Let's call the downward direction as minus. And displacement is positive up direction, 45. So here is minus 5 kilograms, 9.8 multiplied by 45 meters, and that will give you the work that is done by gravity on this particle. Okay, so this is how we calculate the work that is done by gravity. The important thing to remember, solving a work, you're dealing with the force, and it most likely will be a constant force still in many of the examples. And you just need to find out whether that force and displacement are in the same direction or they're in the opposite direction in this case. Okay? All right, so let's take a look at some PowerPoint slides from the book and continue our discussion. All right, so we did derive the kinetic energy and the work starting from Newton's second law, and this was the first figure of force going in the same direction. Now, the one side of the integral, we define work, that is integral of the force respect to the position, right? And as long as they are parallel, anti-parallel, it's simply the magnitude of the force times the displacement. And on the other side of the equation, we have derived and defined the concept called kinetic energy, the energy in motion. Now, the kinetic energy is 1/2 mv squared, that is equal to the work. I'm sorry, the change in kinetic energy. The change in kinetic energy is equal to work. Now, what would be the unit of work then? Take a look at this expression here. The unit of force is Newton, and the unit of displacement is meter. Newton multiplied by meter is equal to joule. Okay, so 1 Newton is kilogram times m meter per second square, right? And then you multiply another meter from the displacement, that's why you have m squared divided by a second square. So 1 joule is equal to 1 kilogram meter square per second square, and that is Newton meter, and is equal to joule. Okay, that's joule is the unit of energy, and work is equivalent to energy. Take a look at this slide here. This case on the left, the work is positive when the force acts in the same direction as the displacement. So you can see here, the force applied here will speed it up as displacement increases. This direction or the opposite direction. As long as the force and displacement directions are in the same direction, the work done is positive, and the opposite, work is negative when the force and displacement are in the opposite directions. And of course, work is zero if the particle doesn't move, and that is very apparent here. Work is force times the displacement. There's a situation where you could have zero work situation, and one here is if there's no displacement, there will be no work done, and if there's no force, if the force here is zero, of course, there's no work done. We will continue these other situation where the work done could be zero, even though both of them are non-zeros in the next lecture. All right, let's take a look at this example over here. So, a 1,000 kilogram elevator accelerates upward at 1.0 meter per second square for 10 meters. starting from rest. Notice there's no time information in the question, but it gives you the displacement. It's asking you to use work and energy concept. A situation here is that you have an elevator, and the tension of the elevator is pulling this up, and the force of gravity is trying to pull this down, and currently it's accelerating upward with acceleration that is positive, going up. Number one, how much work does gravity do on the elevator? It's simply asking the work done by gravity, which is force of gravity times the displacement it causes. Now remember, the directionality matters a lot here. The force of gravity is pointing down this way. The displacement is pointing upward. They are opposite. Okay, so you have to have minus work here, negative work here. So here you have downward force minus mg times positive delta y. So we have minus 1,000 multiplied by 9.8 times 10 meter will give you minus 98,000 joule. Right? 98,000 joule. That is the work done by gravity on the elevator. It causes negative 98,000 joule. B. How much work does a tension in the elevator cable do on the elevator? So take a look at this. We can easily write the sum of forces as tension minus force of gravity causes the elevator to accelerate upward. So here we have tension minus mg is equal to ma. So tension is mg plus a, which is 1,000, 9.8 plus 1.0. That is given up here. So we know that tension, which is a force, is 10.8. One, two, three. There we go. So that is Newton, right? So here is 10.8 times 1,000. You have 10,800 Newton. But it's asking you not for the force, but it's asking for how much work is done by the tension on the elevator. So work done by the tension is tension times the displacement. And in this case, tension and the displacement shares the same direction. So we just calculate this as the tension times delta y, which is 10 meters positive. So work done by the tension is 108,000 joule. And finally, what is the elevator's kinetic energy after traveling 10 meters? All right, so we have the two works calculated individually, so we can find the total work, which is, in this case, the work done by gravity plus work done by tension. The first one you have minus 98,000 plus work done by the tension, 108,000. That leaves you plus 10,000 joule, right? And that is the total work done in a combination of these two forces. And that we know is change in kinetic energy, which is kinetic energy final minus kinetic energy initial. The initial, it starts from rest. So initial, you had no velocity. So this goes away. So simply, you have 10,000 is equal to 1/2 mv final square. So in this case, it's simply just asking the kinetic energy. So it's actually just simply equal to this, right? Because initial is, so our job is actually done. If it will ask for the final velocity, this is how you can go one step further and calculate for the final velocity. Okay, so this is one exercises from the textbook that utilizes the concept that we have just learned in this section. To finish it off, let's take a look at a few more conceptual examples, shall we? So here, Ball A has half the mass and 8 times the kinetic energy of ball B. What is the speed ratio of VA, VB? Alright, so we here recall that the kinetic energy definition is 1/2 mv squared. So kinetic energy of A is simply 1/2 MAVA squared. And the kinetic energy of B is 1/2 MBVB squared. And we have to somehow equate this to have a ratio of the velocities. So we're given two informations here. First of all, let's see, ball has 8 times kinetic energy. So Ka is equal to 8 times Kb. That's the second part, right? 8 times the kinetic energy of B, which is equal to 8 times 1/2 MVVB squared, which is 4 times MVVB squared. And this side of the equation is still 1/2 MAVA squared. Now, we just need to get rid of the masses, then we only have the velocities here. So we're given that the mass A is half the mass of B. So we will substitute that here, 1/2 MB divided by 2. I substituted for MA. VA squared, and here you have 4 times MB VV squared, so you have MB divided by 4 VA squared, 4 MB VB squared. Here MB can go away, and 1/4 will go into here on the other side as 16 VV squared. So you have finally VV squared is 16, so square root of that will give you this, and that is the right answer. Okay, you can take a look at this process in this video, and I will post this directly at these slides on D2L for you to review. Alright, so let's take a look at, I believe this is the last example. 2 equal mass pucks on frictionless ice are pushed toward each other. So you have the same mass M here. By 2 equal but opposite forces. So you have force pushing it this way, and this would be the minus force because the directionality is opposite. And this force is going to cause this puck to have displacement this way, while this one will have a displacement that way. And we are asked, is the total work done by this entire system positive, negative, or 0? Alright, so we have 2 forces, so we will have, let's call this force 1, let's call this force 2, and so you have work done by the force 1, which is, let's call this direction as positive and that direction as negative as usual. So we have simply F1 times the displacement 1, and this will have a positive value because both of them have positive numbers. Work 2 is done by negative force 2. But this is actually the same force here, so we can just get rid of the subscript. I've just put minus sign there. The displacement is going to cause this puck to move the opposite direction, which is minus delta S. And now we can also get rid of the subscript to compare. Minus minus cancels out. This is also positive. So you are adding 2 positive numbers. That would be positive work, total work done. Okay, so hopefully, this examples will help you to solidify the concept that we learned today. Remember, the learning objectives of today. Let's go back to our initial slide here. The learning objectives of today, we learned about what is work and why do we use this concept. Now, the second part of the sentence will become more apparent as we move along with our lectures later on. But today, we learned about the definition of work, and we learn about the definition of a kinetic energy and their relationship. Okay, that's the most important thing. Here in the derivation, we have derived that work is the integration of force with respect to position, and in the simplified case today, it's simply magnitude of force times the displacement. And the other side of the integral, we have derived the kinetic energy. And the important thing for you to remember, take home with, is that the work done by a force on a particle is equivalent to the system's change in kinetic energy. Now, that will be all for our first lecture, and we'll continue with the concept later on in our next video. Thank you so much for your attention, and keep safe and positive out there. See you next time.